Okay, let's get started. So today we're just going to go over exam number 2. So EET325, exam 2. And feel free to ask any questions. Number 1 was given the characteristic equation s to the 4th plus s cubed plus 3s squared plus 2s plus 2. It said determine the number of roots in the right-hand half plane. That hopefully immediately makes you think about, let's go ahead and do Ruth Hurwitz, right? This is a pretty simple one. So we start with our rows. This is the highest order S term. We go all the way down to the S to the 0, and then we alternate terms. We have 1, 3, and 2, and I'm giving myself lots of room so that I can do my calculations here. And then I have 1, 2, and if you need it, 0. To solve for S2, it's -1/1 times the determinant of the first row, or the first column, and the column just to the right. So we're going to do the determinant, which is 2 minus 3, which should be equal to +1. And then the next one we'll do is, again, the first column in the arrow 1. So we have -1/1. And we have 1 times 0, which is 0 minus 2. So 0 minus 2, which is equal to +2. Okay. We move down one row. And if you look really quickly, if you see S to the 1 row, you can see that when you determine the values, it's 1, 1, and 2, 2 are the coefficients. You can already see it's going to be equal to 0. But if you haven't seen it, let's go ahead. We have 1 times 2 minus 2 equals 0. Now, some of you made mistakes of substituting E at this point. You cannot substitute E at this point because you have to check and see what that next number in that row is going to be equal to. Okay, if that is equal to 0, then you can't use that little E approach. You have to use the auxiliary equation. So let's go ahead and do our next step. So we have our values over here. So we have -1/1 times the determinant, and we can substitute in a 0 over here if necessary. We have 1 times 0 minus 1 times 0. So that's going to be equal to 0 as well. So we have 2 zeros in that S to the 1 row. Okay. And maybe I should have mentioned this when we were covering the material, but anytime you have an E or a 0 here, that's not going to be correct. The only time you can use this E approach is for S2 and higher, because this number should always be a 0, right? That term should always be a 0. So we had to use the auxiliary equation. The auxiliary equation means go to the row just above the row of zeros. In this case, it's S2, and grab your coefficients from there. So that becomes S squared, because 1 times S squared is 1, is S squared, plus, and then we skip a term 2, and then we take the derivative of that with respect to S, and that's what our coefficient is going to be, or our coefficients are going to be. We substituted 2 in there. Not an E, but a value of 2. Okay, everybody see that? So now we can continue on. And now we've got our A term here, or let me just go ahead and put this term over here so we have room. So we have -1/2 times 1 times 0, which is 0, minus 2 times 2, which is 4, which is equal to 2. And so now the question is, how many poles in the right-hand half plane? Well, how many sign changes? Positive, 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 and positive. So there are 0 sign changes, which means there are 0 poles in the right-hand half plane. We know because there's a row of zeros here that we're going to have a marginally stable system, but that was not what the question said. It didn't ask how many poles are in the left-hand half plane. It asked how many poles in the right-hand half plane. Are poles on the j omega axis in the right-hand half plane? They are not. They're on the j omega axis. So those do not quantify as making the system to be guaranteed unstable. Remember, we need to know what the input is to assess what the stability is. And then the other thing too is check your results. You had lots of time in the test. I didn't see anybody really do this, but you could have done the Routh-Hurwitz and then check it by doing what are the roots. This is the MATLAB equation or approach. 1, and that would have been fine as well, right? That's a way of checking your Routh-Hurwitz. If you would have seen any poles in the right-hand half plane by plugging this roots function, you would have seen it. Questions on number 1? Was it tricky? Not tricky?
I thought about it as much as I, that's what some of my, when I read the question,
You misinterpreted the question?
all of that is just my, let's say, the way that I was trying to figure out, and that plane, that's all, see how that.
Well, keep in mind, you can't solve for the left-hand half plane with Routh-Hurwitz.
Yeah, I think that's how it's so confused, that I don't know, I said, we read it, not like that.
So you thought I asked for the left-hand half plane?
Yeah, just maybe. So yeah, that's something like that.
I mean, that would be an interesting question. I could say, in this problem in particular, how many poles are in the left-hand half plane, right? How many are there? There are 2. Because there are none in the right-hand half plane, and you know that there are at least 1 on the j omega axis. And the way that you solve for the poles on the j omega axis is you set the auxiliary equation equal to 0. So when you do that, S is going to be equal to plus or minus J, which are 2 poles on the j omega axis. So a more challenging question would have been how many poles in the left-hand half plane. You could have calculated that as being 2. Because you've got a total of 4.
Oh,
because it's S to the 4th, right?
Yeah.
So you know that there are at least, right, and those are poles, yep, not zeros. But I just asked for right-hand half plane, not left. It certainly would have been a little, it would have maybe given you pause to think about it, right? But could have done it.
I would have calculated the whole thing, just find all the poles.
You would have hit the roots equation, the roots function. Yeah, what if I would have said find them using the Routh-Hurwitz? Could you have done that?
Okay, that's a
A little bit more thinking.
more big night.
But the thing I did try that was said Aaron, I just assumed that I don't know what else. I think I just kind of did it wrong.
But you didn't go back and check and see, because usually MATLAB gives you a little bit of a clue as to what the mistake is.
Yeah, I just said invalid. Like I must have just missed like a parenthesis or something.
Okay. Fair enough,
I just can't do it, whatever.
but you should be able to do it. Do we want to see it in MATLAB, or do you feel like everybody could do that pretty quickly?
No, I believe it.
Okay. All right, number 2. I have a system here. Here's K over S times S plus P. Here's a summer. Negative feedback. And here's my input. Here's my output. I said find the value of P so that the system has a less than 5% overshoot and the response time settles to 2% of its final value. Okay, within 4 seconds. So those are both binding requirements. You've got to be less than 5% and less than 4 seconds. All right. So you have to pick the value of P that meets both those criteria. Because to pick the value of P, you might be able to meet one of the criteria, but not the other criteria. So you just need to make sure that you meet both. So very first thing you have to do is solve for the closed loop transfer function, which is going to be equal to G all over 1 plus GH. Right? And I got to do a little math. So this is K over S squared plus PS all over S squared plus PS plus K. Right? And if you remember with second order systems, I'm really focused on the characteristic equation of my system. So all I'm really focused in on is that equation. So I know that S squared plus PS plus K has to equal S squared plus 2 zeta omega sub ns plus omega sub n squared. Well, there was one piece of information, because you had to solve for K and P. Unless I gave you one of those values, you could have had almost an infinite number. So I told you K was equal to 4. So we have S squared plus PS plus 4 equals your zeta, whatever that equation. Well, immediately you can see that omega n squared is equal to 4. So omega sub n is equal to 2, correct? That's your first step. And then your next step is solving for this value of P that meets this criteria. Well, you can see that P is going to be equal to 2 zeta omega sub n. So there are two parameters in there, right? There's zeta and omega sub n. Well, we already solved for omega sub n here, correct? Okay. So now we just have to solve for zeta. And if you remember my peak overshoot equation, maximum percent overshoot is going to be equal to 100 e to the minus pi zeta all over the square root of 1 minus zeta squared. If you solve that equation for zeta, do I need to write it all out, or do you remember how to do that? I mean, if you can't, we can do it out, or is it just tedious to see the math? You good? Okay. So when I solve this for zeta, I calculated zeta is going to be 0.69. That's what I solved for. Okay. But remember this peak overshoot, the peak overshoot has to be less than or equal to this value. Yeah, so M sub P should be less than or equal to 5%. So when you solve that, zeta needs to be greater than or equal to 0.69. So then the only thing to do was to check, because we already knew that this had to be met because we did the calculation. Now we just do our settling time check, which our settling time was supposed to be less than 4 seconds. So let's see, our settling time equation is 4 over zeta omega sub n, which is 4 over 0.69 times 2, which was equal to 2.9 seconds. So your value of P need to be 2 times 0.69 times 2. I had that equal to 2.76. Or maybe I should say greater than 2.76. There are a lot of struggles on this one, and I'm not sure why. Solve for zeta.
Not clearly, stop it, came back to it. Went to the other question, came back to it.
Sure. Yeah, it's not an easy one to solve. Does everybody see the process, though, of how to do this? You had to check to see, because sometimes if you can't get there from here, like maybe your mega cement, maybe that value of K that we picked would be too big. If K was equal to 4, maybe we couldn't get a settling time less than 4 seconds, but in this case, we were able to. So P needed to be greater than 2.76. Well, it's worthwhile, right? You have 2 design criteria, so you should check. Fair, not fair?
What did you say? We know what you said, oh, you want, yeah.
Was it tricky?
Yeah,
What's that?
I should just remember.
Okay. Number 3. So you have a characteristic equation, and I made it much tougher for you because couldn't use your calculator on this one to check. Right? You had a value of K in there, and I said, find the range of K that results in a stable system. Uh, 2s squared, yep. Sorry, I looked at it. So let's start doing Ruth Hurwitz, right? I'm going to start putting our numbers in. We go s to the 5th. So we have a 1. Then we skip a term, so we put the 2 in here. Then we skip a term and put the K. And then we do next 3. And then 7 and 0, correct? Everybody agree with that? I'm really sad.
Yeah.
Did not agree with that
Zero.
because where's the S cubed term? And do you remember the necessary and sufficient conditions? If a term vanishes, or if you have a negative term, system can't be stable. So you didn't have to do anything in this one other than to say the system can never be stable because you don't have an S cubed term.
I got to be one of them.
You didn't need to. You had to do no work. You could have just wrote down, since there's no S cubed term, there's no value of K.
So, you said, on that one, I thought about, like, yeah, that's the difference of it. It was 25. We just think it's not possible because the X is 0. Like, there's no way I can find that would say this. The manufacturer could do, and that's what thinking about it.
So that's the problem, is you're not confident in the material yet, yeah, right? If you know, and we said that those are necessary but insufficient conditions, that you can have no term that vanishes, that's what you say. It is a necessary condition that no term vanishes. Because a term has vanished, it can't be stable. You certainly could have done the next step, right? Which is
Yeah.
and K. And then what you end up over here is -1/3. And the determinant is 2 minus 0. Is there a value of K in there? Plus, minus. And since that value of K is not in there, you're done. There's no value of K that results in a stable system. You don't have to do any more work. You stop right here. Because I can do anything I want to K, and it can never make -2/3 positive. What?
I put it in that map.
Two poles in the right-hand half plane, and they just kept going to the right. So you can't get there from here.
Yeah, but that would be I the problem, and then X 0 equal to the K, which means impossible. And I get the big numbers like, yeah, there's no way. I'm like, it's impossible.
So I put this problem really to make it easy or easier to do. But I also put this problem because if you didn't understand it or confident, it was a pretty tough problem to get there. There was a lot of math and a lot of checking, wasn't it? It wasn't easy.
Yeah.
But if you just, even if you do the Ruth Hurwitz approach, you just needed to stop here. This wasn't a hard a calculation, right? -1/3 times 2 minus 0. The rest gets harder, but this one was pretty easy. Any questions on number 3? Fair, not fair? Was it tricky? It wasn't meant to be tricky. Because you could still do the Ruth Hurwitz. Yeah. It wasn't meant to be tricky. It was just meant to be like, wow, if you see it, you get it done. All right, number 4. We had some summers here. G1, G2, G3. This was plus minus. G5. G4. There were a lot of struggles on this one. I was surprised. I thought because I made this one a pretty hopefully straightforward one.
No,
What's that?
no.
You didn't have to move any pickoff points. You just have to combine stuff and cascade. So here is negative feedback in cascade with that. So I'll rewrite that. Summer. This becomes G1 over 1 plus G1, G3, all times G2. Here's G4. And G5. Now I need to put these two, which are feedback blocks. So let's do the math a little bit. So we have G1, G2 over 1 plus G1, G3, all over 1 plus G1, G2 over 1 plus G1, G3 times G4. So that's going to be equal to G1, G2 over 1 plus G1, G3, all over 1 plus G1, G3, plus G1, G2, G4, all over 1 plus G1, G3. Now I invert multiply. G1, G2, all over 1 plus G1, G3, plus G1, G2, G4. And now all I'm left with is that one final block. I don't know if I gave myself a lot of room, but that's okay. So I have G1, G2, all over 1 plus G1, G3, plus G1, G2, G4, and then that cascades into G5. So my final one is G1. This is the open loop or closed loop transfer function. G5 all over 1 plus G1, G3 plus G1, G2, G4. Questions on number 4? Fair, not fair? Dumb mistakes?
Yeah, I could. Move something for the numerator. Yeah,
Ah.
it's all like that.
Okay, algebra, right? This can get tricky on algebra for sure.
Skip steps.
Yeah, write it out. If you write it out, it's hopefully easier to see. Hopefully. Last one. 2 over s squared plus 2s plus 4. Solve for zeta, omega sub n, and omega sub d. We know that s squared plus 2s plus 4 has to equal s squared plus 2 zeta omega sub n s plus omega sub n squared. So immediately, omega sub n was going to equal 4, which means omega sub n is equal to 2. Right? Once we have that, 2 is going to be equal to 2 zeta omega sub n. So zeta is equal to 1 over omega sub n, 1 over 2, which is equal to 0.5. And then the only thing that you had to have the equation for was a damped natural frequency. So I'll show you the actual equation. So this is omega sub n times 1 minus zeta squared. So that's equal to 1.73. If you didn't have the omega sub d equation, all you needed to do was remember is when you convert this to s plus alpha squared plus or minus omega sub d, right? Or plus, I should say. Erase that. So it's omega sub d. It's not working now. Oop. This is seemingly falling asleep. Well, maybe, oh, there we go. Took a second. So this is omega sub d squared. So all you needed to do was do the quadratic equation, right? Negative b. So negative b is equal to negative 2 zeta omega sub n plus minus, this is really slow, b squared minus 4ac minus 4ac all over 2a. That's the general equation. So then we cancel out some terms here. So we have negative zeta omega sub n plus minus. Now I'm going to move, well, I'll keep the 2 over here. So I have 2 zeta omega sub n squared. Or not omega sub n squared. It's 4 because this whole thing is squared. Wow, this is really slow. Right? And so then this is all divided by 2. So we can move the 2 in here and we're canceling that. So then we see we have plus or minus omega sub n squared. This is omega sub n, right? Squared. So I have zeta squared, omega sub n squared. So I can factor out omega sub n. And then I'm left with zeta squared minus 1. If zeta is less than 1, it's a complex number. So we'll assume it's a complex number. So this becomes plus minus omega sub n with the j term out front, 1 minus zeta squared. That is omega sub d. So you could have solved it that way as well if you couldn't remember how to get it. You're just looking for the actual oscillating or oscillatory frequency for the system. And that's it for the test. Too hard, too easy, just right. The grades would have been indicated that it either was too easy or that you understood this material pretty well. So which one is it? What's that?
Fair.
The test was fair? Did you understand the material really well? It's a binary choice.
Yes, I could say Like, last we gave us those 2 3 weeks ago. I would have failed it. Not a problem.
Well, that was during break, so for sure, right? But is this the type of test you want to see in the third test, or you want to see more complicated, or? Pardon? Well, but also you want to make sure you learn the material. So do you feel like the test is an accurate indicator to assess what you've learned for the material we've covered thus far? That's really what the test is supposed to do. It's not supposed to punish you. It's just a means to assess, did you learn the material? If you feel like that's the case, then it's not too easy of a test. If you feel like, no, it needed to have more rigor or it needed more questions, then that's a different.
I totally forgot about the information.
But do you feel like it's an adequate assessment tool to see what you learned? That's the key thing. TV Land, do you have any opinions? Oh, you let us know. Have to drive to Boston to take it?
Yeah, there's no more important until July.
Oh. They used to have one in Bangor, but that's closed now too, so.
No, they have. They don't have.
Oh, really? Okay. They had one in Augusta. Maybe the one in Augusta closed.
Yeah, I think that's the one. Next week.
Okay. You just signed up late, it sounds like.
But I live in New York, so the whole weekend.
Only an hour drive to Beantown, so. Any comments or questions from TV Land? Nothing?
I didn't think it was easy, but I think it was fair.
Okay, and you feel like it was an adequate assessment tool of what you think you should have learned based on what we've done?
Yeah. Yeah, definitely.
Okay. Yes, sir.
I can bring, I have the
Booklet?
booklet. Can I bring that?
No.
No.
Bring it with you, but I think they'll give you a new one, or I think it's actually online. You have to do it online.
Yeah, okay.
Yeah, they give you all new materials so that you can't. Because you could write in the booklet, you could write whatever you wanted. Yes, but they're like $8. I mean, ask him if he can use MATLAB.
You got it. I think.
No, they won't.
No, I don't think so.
All right, everybody, like I promised, I'm not gonna slow down a little bit this semester, as long as you're okay with it. I'm happy to cover new material, but slow down and just go over the test. So give you a chance to breathe and. Okay. All right, have a great day, and I'll see you all on Tuesday. Take care, everyone.